Welcome everyone. This is Adarsh. Today we are discussing about attention multi-view stereo. First we can discuss about stereo vision and its terminologies. Stereo vision means two or more cameras acquire image from different point of view. Then the disparity map of this image is calculated. From the disparity, depth of each point of object from the camera is calculated. A 3D shape of object is recreated using computer graphics using this 3D point cloud obtained. Normally we call this process as stereophotogrammetry. Coming to multi-view stereo. Normally in the case of two camera stereo we use only two images for the depth calculation. In the case of multi-view stereo camera we use multiple cameras to capture more viewpoint to increase the robustness. Coming to stereo vision, we have to solve two problems. First one is the correspondence problem and other one is the reconstruction problem. Correspondence problem means point in an image will have a corresponding point in the other image which need to be find out to calculate the disparity. In the reconstruction means we need the we need to recreate the 3D shape of the object from the point cloud for various applications. Correspondence problem. Correspondence problem mainly there are two types of technique, correlation based technique and feature based technique. The correlation based technique attempted to establish a correspondence match by matching the intensities. In the case of feature based technique, it attempted to establish a correspondence match by using image features. Example of an image feature is a corner. The basic configuration of a stereo camera. Here left camera and right camera are placed at a distance. The distance between the left camera and the right camera is called baseline, and this point is actually the object placed in front of the camera. Here we can see a shaded region which is called epipolar plane, which means that plane passing through the optical centers and a point in the scene. Then another terminology is the epipolar lines. Intersection of epipolar plane with the image plane is called epipolar lines. The basic principle underlying the stereo vision is the triangulation. From the basic principle of similar triangle properties, we calculated the disparity and also the depth from the camera. Here D represents the disparity equal to XL minus XR. These are XL and XR, which is normally obtained as in terms of pixels. So we need to convert into mm or whatever measure, we need to multiply with the pixel width. We can calculate the depth using this equation obtained from the similar triangle properties. Z is equal to TF divided by D into P. In the case of multi-view stereo, we need to face lot of issues. Some of the major problems the paper trying to solve are the perpetual features learned from the image to construct good matching confidence. How can we utilize fully this perpetual feature? And the second one is how effectively we can aggregate and regularize the matching confidence. And the third problem the paper trying to solve is how can we improve the quality of the training data. The major contributions of this paper are, first one is they design an attention enhanced matching confidence volume which take account of both the perpetual information and contextual information of a scene to improve the matching robustness. Second one is they are introduced a novel attention guided regularization And the third contribution is actually they introduce an effective filtering strategy to improve the quality of the image. This is the basic architecture of the attention multi-view stereo described in their paper. It have basically four steps: input feature extractor, attention enhanced confidence volume, and the attention guided regularization and depth regression. We can discuss about each of this in details. The first stage of the architecture is feature extractor. The feature extractor is aimed to extract the perpetual feature from the input image, which is done using an encoder network which consists of 10 layers. Here, they used an instant normalization and ReLU in the stage. Next stage is attention enhanced confidence volume stage. Here, Here we convert the extracted feature map into individual channel descriptor via global average pooling. From that, we can calculate the contextual channel-wise statistics WV of the local scene using the equation. Then, from that, we can calculate the attention channel weight vector WV star from the skews and excitation block. From the attention enhanced matching confidence from the equation given. After that, star called the attention enhanced confidence map along the depth direction to produce an attention enhanced matching confidence volume M star, which is then fed into regularization module. Next stage is attention guided regularization. First, we encoded the M star, the attention enhanced matching confidence volume, into two unregularized matching confidence volume R0 dash and R1 dash via two convolution block with stride 1 and 2 respectively. After that, regularization process starts with the R3 dash on level 3 based on the multiple ray fusion module RMS, which has upsampling and downsampling and also have a RAM module. Here we use on simple RMF also. Simple RMF keeps a residual connection from second layer to fifth one, but no RAM and upsampling and downsampling operation. The RFM module have a pre-contextual understanding module and post-contextual understanding module. Next stage is depth regression and loss. After obtaining the regularized R0, a three-dimensional convolution layer is encoded into a depth probability volume V. The depth probability volume V is used for calculating the depth using softmax operation. After obtaining all depth map, we could directly use depth map filtering and a fusion method developed into reconstruct a complete 3D point cloud. We can generate a 3D model from the 3D point cloud using computer graphics. In the last stage, I explained about the depth map filtering strategy. I am going to explain it in details. Depth map filtering strategy. The captured point cloud is passed through the Poisson's mesh, which is highly accurate but incomplete rendered raw depth map containing outliers. This, this raw depth map is compared with the visibility depth map to obtain an improved depth map. This improved depth map is our actual output we used for 3D reconstruction. Harish will explain about the evaluation and the result.
Hi everyone, this is Harish and we'll be discussing about the experimental results of this paper. In this we have primarily three sections. One is to improve the ground truth of the depth maps. Second is regarding the model training and the third is regarding the ablation study. On the first point, we are evaluating the performance of the model on two benchmarks. The primary one is the DTU benchmark. It is a widely used MBS benchmark and it contains about 123 scenes captured in varying lighting conditions. Each scan consists of a reference point cloud having 49 or 64 captured images and their corresponding camera parameters. But the issue with this benchmarking criteria is that it cannot be directly used by the usual depth map based methods for network training, and one need to generate the corresponding depth maps from provided reference point clouds. In this case, we use the MVS net deep inference for unstructured multi-view stereo. And the working of this is that for each scan, it will produce and train the mesh surface based on the screen Poisson surface construction algorithm. It then renders the corresponding depth maps according to the camera parameters from different viewpoints, which is regarded as the raw depth maps. Raw depth maps could also contain outliers due to incomplete information and incorrect collision relationship, which usually hinders the training performance of our networks. This is an efficient depth filtering method to improve the quality of the depth maps. The image shown here is a evident proof of the output of and the efficiency of our filtering method. The first row contains the input image. Second depth map, we can see that there are outliers which needs to be improved. And in the third row, we can see that our method is able to filter the ground truth depth maps. So this is the basic filtering strategy that is used here. Here we are mixing two depth maps and create, that is a raw depth map and visibility depth which is obtained from the captured point cloud and the image cameras. It is merged and an improved depth map is created. Here the filtering details are shown. The depth map D star is created from the DR and dB as shown in the equation. Here n is the threshold to control the completeness of the filtered depth map. So let's come to the second part of the experimental research. It's the model training part. Here we have trained the model on using PyTorch and on the DTU dataset. We have used Adam optimizer with batch size of 2 and the initial rate is 10 raised to 3 and decay rate of 0.85 till 11 epochs. Each training sample consists of one reference image and two source images, and it contains a set of depth of 256 frontal-parallel hypothesized depth planes uniformly sampled from the two values. All images are resized and cropped to height 512 and 640. Since the homography transformation is very time consuming in case of CPU, the author has pre-calculated the homographic transformation and it has reduced the training time to two-thirds of the actual time. The GPU used here was the Titan NVIDIA RTX GPU model with 20 epochs and it ran for nearly 20 days. Ablation study is done to verify the performance of the feature extractor and attention enhanced matching conference volume, and attention guided regulator module is the proposed MBS. The evaluation metrics used here is the mean absolute depth error and the prediction precision, which is the percentage of the number of pixels where the absolute error of the predicted depth is less than an error threshold to the total number of valid pixels in the ground truth depth map. This slide defines how the model training was done on using the original feature extractor and row matching confidence. The table shows the performance of the model. Here it can be seen that our model has outperformed better. Here the prediction precision has increased from 83.1111 to 87.61 with t equal to 3 and 95.7 accuracy. Now we compare our model with other models. The procedure used is to infer the that maps of all images to each scan from the DTU evaluation set firstly, and then fuse all related depth maps to recover the corresponding three-dimensional point cloud for each scan. Evaluation measures used here are the accuracy and completeness of the reconstructed three-dimensional point, and the MATLAB code was to run to perform the evaluation. The table evidently shows that our attention-based MBS has outperformed other models in a significant number. By increasing the value of Z, we have seen that the overall improvement in the performance. The quality of ATM EVS reconstruction can be greatly improved with the increase in the number of hypothesized depth planes. Also, it can be improved by the depth map refinement process for the attention-based MBS with Z equal to 384. Such a refinement step can further improve the reconstruction quality. So this is the output that we obtained on the scan 77 image, where you can see the reference image at the top, which is a glass of jar. The other methods was not able to completely reconstruct the image. Our filtering method has reconstructed the image completely. The other data sets we used was the tanks and tables benchmark. This is also a large MBS benchmark which has two sequences, one is the intermediate and the advanced. It is captured from realistic environments under different weather conditions. The evaluation metric used here is the F-score, which takes both the accuracy as well as the completeness of the object, reconstruction of the object from the image. So here we are trying to reconstruct the 3D image of a statue. The depth maps evaluated are shown on the right, and C shows the improved depth map of the filtering algorithm. D is a finely recovered 3D model. As mentioned earlier, we sampled the inferred depth maps back to input resolution and has improved the performance. This slide shows that for the intermediate sequences, the ATS was able to give very good results. B, D, C are part of the intermediate sequences and it has performed very well. A is part of the advanced sequences, and it is observed that it is reconstructed the 3D image very well. An appreciable performance has happened on the advanced sequences as well. But the limitations of the GPU is a negative factor for this model, as it was not able to completely do the advanced sequencing. To conclude, in this paper we have brought in a novel attention-aware MBS network. This network has improved matching robustness by attention-enhanced matching confidence volume. This combines the contextual information of the scene and along to the raw pixel-wise matching volume through an adaptive weighting approach, and the corresponding attention-guided regularization module can hierarchically aggregate and regularize the matching confidence volume in a deep manner. The proposed method is simple but effective filtering strategy to enhance the quality of ground truth depth maps for network training. We have also demonstrated the excellent performance of the proposed attention MBS on the tank and timbers dataset as well as the DTU benchmarks. These are the references. Thank you everyone.